Hi all, welcome back to another video. So today we're going to start looking at some more of our linear programming and we're going to start looking at feasible regions. So just a quick reminder of how my notes work. So black writing is a bit of background information, pink writing is key information. It'd be good to note it down if this is what you're doing, if you're note taking. If you're just here to watch, welcome. Blue writing areas are my examples, and then diagrams help paint pictures, so they're good to note down as well if you are noting down. So in maths, we've seen and graphed and solved linear equations in a bunch of different forms. So y equals mx plus c, that's our slope-intercept form, or x plus y equals c, which is sort of our general form of a linear equation. But when we apply linear equations to real-world contexts, some solutions might not actually be feasible. They might not actually fit into the criteria of the context of the question. So a little bit of an example of this. If we have one sausage roll costing $3 and a tray of chips costing $6, how many of each could you buy with $24? Now let's have a little bit of a think about that. So $24 we have to spend. Now we could buy 8 sausage rolls with $24, 3 times 8. We could buy four trays of chips, so 4 trays of chips. But what if we combine them? So we could buy 3 trays of chips and 2 sausage rolls. Okay, so there's lots of different combinations we can look at. So if we actually looking at all these combinations, we can come down here and actually graph these scenarios. So I've let my y-axis be my trays of chips and my x-axis be my sausage rolls, okay? 8 sausage rolls, no trays of chips. 4 trays of chips, no sausage rolls. And then we've got 2 and 3, 4 and 2, 6 and 1. They're our other solutions. But what about these points here? How much does this point here cost? So all of these points cost my exact $24. But what if I have 1 sausage roll and 1 tray of chips? Now remember, a sausage roll is $3 and a tray of chips is $6. So if this point is 1, 1, this solution only cost me $9. Now we have $24, so this is a reasonable answer. We just have some change left over. But what about up here when I have 6 sausage rolls and 4 trays of chips? Now, quick maths, 6 times 3 is 18, so $18 is spent on sausage rolls. And then we've got $24 spent on just trays of chips. Now, 18 plus 24, that's more than 24. So we can't actually afford this solution. And what you will find is anything above this line here, we can't afford. It's more than 24. So this is sort of my constraint, okay? Now, we said a tray of chips was $6 and a sausage roll was $3. So 3 times the amount of sausage rolls plus 6 times the amount of chips, that has to equal $24. So that is how we get this equation here. So sausage roll was X, tray of chips was Y, and my maximum amount of that can be is 24. Now, because we're looking at feasibility, remember above the line wasn't feasible, it cost too much money. So what we have to do, we have to write a constraint. So we have to say that the amount of sausage rolls we buy and the amount of chips we buy has to equal less than $24, or it could be equal to $24. That's where we have our less than or equal to sign. But you've also got to remember, we can't have a negative amount of sausage rolls or a negative amount of trays of chips. So they have to be above or equal to 0 as well. Okay, so our feasible region is the area above the x and the y axis, but below my line that I've drawn. So my feasible region, all my feasible solutions are in this shaded region here. All of the solutions in there or on the lines are feasible solutions. Okay, so this is what we say when we sketch the feasible region, which is what we're going to do another example of below. All right, so graph the following constraints and shade the feasible region. Now we've got x is greater than or equal to 0, y is greater than or equal to 0, and then we've got 2 equations. So 2x plus y is less than or equal to 6, and x plus 2y is less than or equal to 8. So remember, when we're graphing linear equations, we only need 2 points. the x-intercept and the y-intercept. So if we're looking at 2x plus y, and we're going to look at equals 6. So we've got our constraint less than or equal to, but we still work with the equation as if it's equal to 6. Now, x-intercept is when y equals 0, so this implies x is equal to 3. I can trust that you can solve for these by now. So y-intercept when x equals 0, y equals 6. Now let's do the second one, x plus 2y is equal to 8. When y equals 0, x is equal to 8. When x is equal to 0, y is equal to 4. So we have our 2 points for each equation. So we're going to do the first one in pink. So x equals 3, y equals 6. So x equals 3, y equals 6, and we draw a line through them. All right, so then we label our graph. So 2x plus y equals 6. Now my second one I'm going to do in red. So y equals 4, x equals 8. So we go here and here. So let's draw an equation or a line through there and make sure we're labeling. So x plus 2y equals 8. So it's really obvious which one's which. Now, this is where we check our constraints. So we're going to shade our feasible region. So going back up to the top, x is greater than or equal to 0, y is greater than or equal to 0, and then we're less than or equal to our 2 in our equation. So that means it's going to be below the line. So what we need to do, we need to look at what region satisfies all conditions. Now, above the x-axis is all of this above here. To the positive y-axis is all of this here. So it could be anywhere in this quadrant. Now we need to be less than both of our lines. So it could be in this region, less than the pink line. And it could be in this region here, less than the red line. But the only spot that satisfies all conditions is this region in here. Okay, so it is below the pink line, is below the red line, and is above both my x and my y axis. Okay, so you've got to keep an eye on your conditions to shade the appropriate feasible region. Hopefully you got something out of this video, and we'll see you guys in the